Local linearization approximation. For local linearization approximation, we're approximating values that we don't necessarily know the exact value of, but we can get closer and closer to that value to kind of approximate it. So in the picture here, the magnified portions, so the pictures of y equals x squared plus 1. And if I went in very, very close to those magnified areas, it almost looks like I have a straight line. And those straight lines, I could actually draw lines off of those points known as our tangent line. And if I asked you to find the tangent line of a graph, you would, for me, go through and you would find first the derivative at that point. So let's say we want to find the tangent of the graph at x equals a. Then we would go through and find out f of a, we'd need to know. And we'd put together, and we need then f prime of a for our slope. That would be our slope of our tangent line. And then we'd put it all together with y minus f of a equals f prime of a times x minus a. And so that's just the graph of a tangent line there, the equation of a tangent line in point slope form. Well, we use this equation in our linear approximation. This is actually our equation for linear approximation with just one thing altered. So I'm going to highlight this equation for a minute and go to the next page. And here's our linear approximation equation, and the only thing that's altered is I brought my f of a over to the other side. So now I have, instead of y, I'm going to keep it as, I'm going to change it to be L of x. I'll rewrite it a little bit bigger. L of x is equal to f of a plus f prime of a times x minus a. So all I did was use my equation of my tangent line to determine my linear approximation equation that I'm going to use. And again, linear approximation helps us decide it helps us figure out a point that is very close to a point that we're trying to get. So our next piece is, let's see how we use it. And the other bit that I want to go over is with linear approximation, because I'm approximating, I'm going to quickly draw a couple graphs. I'm approximating, and my graphs might be down like that, or as in the x squared one, would be coming up. If I'm approximating along here, I know that I've over-approximated. Over-approximation happens when my second derivative, notice I'm concave down, so that's when my second derivative, f double prime of x, is less than 0. But I've under-approximated because my line would be underneath the curve when my f double prime of x is greater than 0. So those are how we tell our under and over approximations. So let's try a linear approximation. Let's say we have the graph. We're going to find a local linear approximation for the function f of x is equal to the square root of x plus 3. And I want to use at a equals 1, because when a equals 1, we can approximate our function. We know or x equals 1, we know that our function would be equal to 4, which we get 2. So we're going to use it to approximate what the square root of 3.98 would be and square root of 4.05. So to do that, I do need to find my derivative. So I have my equation, L of x is equal to f of a plus f prime of a times x minus A. So my f prime of A, that's one of the first steps I go and find. F prime of A is equal to 1 over 2 root x plus 3. And the derivative of root x plus 3 is still saying it's 1, so it stays as is. So I'm going to find f prime of 1 is equal to 1 over 2 times the square root of 1 plus 3. And this really should be a. So that equals 2 times 4 is 1 over 4. And my f of A is 2. So f of 1 is really just 1 plus 3. Let's take the square root, we get 2. So now we're going to plug this all together. And I have L of, we'll do it with 1, equal to, and so I want to approximate first and foremost this, and I'm going to use that piece as my A, or my X. So what I'm going to do then is f of A is 2 plus 1/4 times 3.98 minus 2. So I really have L of 1 is equal to 2 plus 1/4 times 1.98. And from here I do go, and I can make sure I get my math correct by doing 1/4 times 1.98. So L of 1 is equal to 2.495. Sorry, that shouldn't be 1. It should be our approximation that we're plugging in here. So it's whatever we plugged in for our approximation is equal to that. So my approximation in this case would have been L of 3.98. So, and then I can go and find out if I over-approximated it or under-approximated it by looking at my square root, my second derivative. And I know that this is a square root function, so it faces downward, so I know that I over-approximated. We can do the same thing for 4.05, except now you're plugging 4.05 into there instead of our, so L of 4.05 is equal to 2 plus 1/4 4.05 minus 2. And 2 plus 1/4 times 2.05. And this becomes 2.5125. And again, we can say we over-approximated because it's concave down. Alright, so this just gives you a little bit of a heads up of what linear approximation is, and really it's just the tangent line. Ask questions in class, that way I know what we need to be working on.